So you can start.
All right, great. So welcome back, everyone. I mean, this has been really an amazing conference. I've gotten a lot out of this, and it's great to see everyone over Zoom. Some of you who I haven't seen in a couple of years. For the last session today, it's going to be focused on substellar and stellar companions, and we have quite fascinating series of talks here at the end. So we've saved, I think, some of the best ones for last. But what's sort of interesting about this is, I think a lot of the conference up to now, if you pick a companion mass and you higher and higher in that companion mass, it becomes easier and easier to survive common envelope evolution and emerge as a type binary. And of course, with observations, we see those things and they're easy to say, okay, it comes from here. But as you go the other way and you lower and lower and lower the companion mass down into low mass stars like M dwarfs, and then into things that, substellar like brown dwarfs and planets, it's interesting to sort of ask some questions about, what does happen. So, and so I just have a couple of slides here, just some general things to get a discussion started, and then just to highlight some recent work that a former graduate student of mine who just graduated last month, some papers of his. But the first thing I wanted to just say is, so for instance, we know substellar objects are plentiful around stars, especially planets, right? They're around main sequence stars. They might be around all main sequence stars or half of main sequence stars. And we've known about this for a while. And just to highlight this, this is a figure from a paper I did a long time ago. At the time, this was all known planetary systems around main sequence stars, and you can evolve the orbits, and you can incorporate the evolution of the system, mass loss and tides, and all that in. And then you can predict what happens to those planets. And so here, anything that's a red dot will plunge into its host star as it evolves off the main sequence. And anything here that's a blue dot, it gets pushed out to sort of where the green dots are. And so already, a decade ago, we're seeing that we've got this large reservoir of things that will just like plunge into their stars. And so they may not survive. They probably won't. I mean, maybe the most massive could, but if you're a typical Jupiter, a few Jupiters, you on your own won't have enough energy to survive. But it's interesting to sort of think about what are some of the effects of it. How does it affect the giant star that it becomes, or does it stir up some mixing in the star? Does it change the isotopic abundances? So do we observe those? Does it spin up the rotation rates a bit? What happens to it once it's sort of inside the giant? Now we also know that some substellar objects can actually emerge from common envelopes into post-CE orbits. There's a handful of brown dwarfs that are in sub-day periods around white dwarfs that are known to survive. In those systems too, it's thought that they haven't undergone much evolution during that phase. Their initial mass was whatever it was, and it emerged at about the same initial mass. So they seem to be sort of unfazed by it, but they have emerged on their side. And then recently, which is really exciting, we have one planet now. So we have one planet in a substellar or a sub-CE orbit, a short period orbit. And so the first two talks of this session will be on that particular one. So it is really interesting to think about these questions a bit. And even as you go up to things above substellar objects like M dwarfs, like really low mass M dwarfs, we know those emerge in short period orbits around white dwarfs. Some of them won't. Some of them will be destroyed during this process of CE. And so to think about, all the different potential outcomes as you scale the mass down, scale the mass of companion down, I think it's sort of an area where it gets some thought, but there's probably a lot more that could be done. And so for this session, I'm at least hoping to get out some discussion of how do these things affect CE evolution? How can we connect them to observations? What can we infer about it, about that evolution? And sometimes it might be a very minor thing. I mean, it may be something like, okay, you get, the isotopic abundances change, but in others, it may be something a bit more drastic. And I did want to highlight some work my group has done in the last few years on an outcome here where we think it very much does change the outcome of the system. And that's in terms of the magnetization of the white dwarf itself. And so there's a whole class of white dwarfs, which are called high field magnetic white dwarfs. And these things have field strengths from a few to up to 1,000 megagauss. And so these are like super magnetized white dwarfs. they're the white dwarf equivalent of a magnetar, essentially, for neutron stars. And about 10% of white dwarfs are highly magnetized in this range. And what was really interesting was about a decade ago, and a little bit more than a decade ago, SDSS had some observations that really constrains the type of systems that these things are coming from. And it was linked to binarity. And so if you look just at sort of isolated white dwarfs, and you look at white dwarfs that are in detached binaries with things like M dwarfs, if sort of the magnetization was independent of some sort of binary interaction, then you'd expect the distribution of fields in those two systems to be the same, and yet they're not. And what's really interesting is you don't see, it's extremely rare for a white dwarf, M dwarf system that's detached and separated. It's extremely rare for that white dwarf to ever be magnetized. And yet when we see white dwarfs by themselves, there's a huge number of them that are highly magnetized. And so maybe your first thought is like, oh, that's sort of weird. The logic is a little bit maybe different. And we pitched this idea again a decade ago now in PNAS that actually has to do with removal of the M dwarf from the system. And so the idea is that if you're a slightly more massive star and you've got a low mass M dwarf sitting around you, if you gobble that thing up and it doesn't have enough energy to survive the interaction, it works its way down to the center of the core there, and then it tidally disrupts. And then you've got an accretion disk inside the star that's around what's the proto white dwarf, and that accretion disk then can do things. It might amplify magnetic fields, and it might transport to the surface of the white dwarf. This is very speculative paper, but interesting, I think. And so anyway, the theoretical idea was put forward in this first paper, and there were several caveats to it, because this accretion disk in particular is very different from accretion disks that we typically think of. So it's sitting down on the inside of the giant star, which is, it's bathed in this like super hot thermal bath. The disk is very cold. So the disk, might be 10 to the 3, 10 to the 4 K, but the ambient at that point is 10 to the 7, 10 to the 8 K. So one of the caveats right from the beginning was like, okay, you throw a disk down in the star, does it even survive? Is it just thermal entrainment, just sort of gobble it up and mix it up before it could even maybe rotate once? Because if the disk can't rotate once, it can't amplify magnetic field. You need at least a few rotation times to saturate a field. So the very first question we were interested in is, does the disk even last that long? And so we did some simulations of this in 2 papers, and I think it was Morgan, I think, at the beginning of the conference, if I remember correctly, was talking a bit about what's really interesting is we can't do from with binaries not touching, then you get unstable mass transfer, then it goes to CE, then it emerges as the binary. Doing that entire problem from start to finish is sort of not realistic computationally. But what is really nice is if you can chunk it up into different parts, what can you learn about those different parts in more detail? And I think this sort of approach is a very similar idea. And so what we did first is we said, don't worry about the common envelope. First, let's just put a hockey puck that's consistent with the mass of the disk down in the center of a star. So we did typically what you normally would do. We put a star on the grid, except we didn't hydrostatically put the entire star. We put just the inner part of the star. So the inner 10 to the 12 centimeters, essentially. So 10 to 20 to 30 times smaller than you would start it normally. And we just wanted to say, okay, it's got consistent mass. It's got sort of, it gets compressed a bit from pressure. It's got its proper structure. Let's just see if this thing goes, and let's just watch if it heats up and sort of mixes in with the stellar ambient fast. And so this is the first one here. And there is mixing. There's the angular momentum transport is mostly in the surface layers of the disk, where it's shearing with the stellar ambient. But you can see it's a very cold disk sitting in this thermal bath, and yet it can last. I think this one we simulate out to 10 full rotation periods of the outer disk, the outer edge of the disk, and you can calculate the mass loss rate from the disk essentially as it gets mixed in the ambient. And we sort of said that the disk would at least last 100 rotation times before it's fully mixed in. And this might be difficult to see here. You'll see it in the next one, but the total physical time of this system is like a day, right? So this is a very fast process that's happening on, time scale of about a day. And that was the first paper we did a couple of years ago. And then we wanted to take it back up one more step and say, okay, we're pretty sure like if we get a disk down there, it'll survive. Now let's actually see what it looks like if we set up an actual planet or brown dwarf on the grid with its full structure so that it's hydrostatic, and we let it go into the thing, and can we get it to tidally disrupt around the core of the star? And what does the disk that results from that look like? And so this next paper, which we just put out a couple months ago, does exactly that. We resolve the full structure of the companion on the grid. So we're not using a point particle at all. We're actually setting it up so it's stable, just in the same way we set up the star to be stable. And then we let that thing go, and we give it some eccentricity, because otherwise, and we start it right at about where it should tidally disrupt. And if we move it out and don't give it any eccentricity, it does several orbits, and the computations just become too long. So we give it a little bit of eccentricity, a 0.3, so let it move in a little bit, and you'll just see it disrupt on the first orbit. And so I'll play this one now. And so it's tidally disrupting again, and you know, oh geez, did that stop? That seems to stop on my end. That's let me see. Oh crap, my computer freeze. Okay. Oh, I don't know what just happened there. Let me try this again though. Maybe that was a bit too much. Okay, let's try this one more time here. What you actually see is that as the thing tidally disrupts, about half of it has positive angular momentum and wants to move outward. About half of the gas has negative angular momentum and moves inward. And it does it very rapidly, and it sort of fills in that inner portion there. And so even though maybe the disk doesn't look exactly like the disk that we had started with from the previous paper, you definitely get a disk here structured down in the center from a tidally destroyed brown dwarf or planet. And so that's really interesting, because you can ask the question is, how does that affect the white dwarf itself? Maybe it can add a little accretion to it, so it creates some additional mass. There's extra burning that might go down on the center. And of course, if that disk, if we do a simulation of this, with MHD, question would be like, what field strength do you grow in this situation, and what, and can you actually invect that thing to the surface of the white dwarf and anchor it there? And so even though this system would not result in the star sort of shedding its envelope, you wait the requisite 10 to the 5 years for an AGB star, and what emerges at the other end is a magnetized core. And so I just sort of think that scenario is interesting. And there are probably a lot of other scenarios too, with these companions that don't quite eject the core, but have other impacts on the giant in the system. And then the question is like, what impacts are those? Can you connect it to observations, and how can theory and observations interact in that space? So that's really all I wanted to say on that topic. Let's see, how do I stop? There we go. So we could either have a brief discussion here on that now, or we could just go straight to the talks and leave the discussion for after after the talks. All right, well, maybe we'll just hear the first set of talks, and of course, any questions on any of this at any point is welcome. So I think our first speaker today is Luke, and he's going to be talking about this planet in a short period orbit around a white dwarf that I mentioned. Luke, I'll tell you 2 minutes. I'll give you a 2-minute warning.
Sure, thanks, Jason. So this work that I'll be talking about was done in collaboration with the 2 Rochester, New York institutes, right? The one I'm at, University of Rochester, and then the one Jason's at, RIT. So Yeah, primarily I'll discuss this model relating, I mean, at least it's motivated by this object, this planet that's orbiting a white dwarf. So this is an artist's rendition of it. It has a period of 1.4 days, which translates, if it's a circular orbit, it translates to a distance of about 4 solar radii. Has a cooling age of about 6 gigayears, so quite old. And all of this is in a paper, this paper here. And there's constraints on the mass of the planet of about somewhere between 1 and 10 Jupiter masses. We know the radius, but the mass is not fully known. And there's an update on this paper that's not out yet, but that was shared with me, so the data is a bit better. There was also another object, which is a more indirect observation of a planet, but believed to be a planet at least. Accreting, the white dwarf is accreting material, and it's believed that it comes from maybe a Neptune-sized planet, and that's in this paper here, and that has a much shorter cooling age. Now, it's when this paper came out, it was speculated that the scenario that works the best is a perturbation. Now, this system also has 2 M-dwarf stars orbiting each other at a much larger distance, and there were several papers that came out saying that there could have been a perturbation of the planet's orbit after the white dwarf was already there. So, and by this Kozai-Leadov mechanism, and the planet would have gone into a very eccentric orbit, and gradually it would have circularized close to the white dwarf. So that's sort of the alternate or theory about this. But then common envelope, I don't think at all can be ruled out, and in some ways it's simpler, and it's much better possibly at explaining the second object, which is a very young object, okay, where maybe the Kozai-Leadov model wouldn't work as well. So you hear from me, and then you'll hear from another talk right after mine, looking at this source and the common envelope. So in our model, we don't believe that, we find it very difficult for the planet to just simply eject the common envelope. It's just, it doesn't get down deep enough, and the planet is not massive enough. So our model works this way. We have 2 objects, a previous planet, the blue one, or planet, or even possibly a brown dwarf, or even an M dwarf, as you'll see, I'll discuss later, that actually that undergoes common envelope first. And what actually happens to it is it gets shredded, just like Jason was talking about, gets tidally shredded, and it accretes onto the white dwarf. And in doing so, it releases a lot of energy. It puffs out the star. And of course, it would have caused some expansion even before that. But if it's small enough, most of that expansion would happen on the while it's accreting. And because it puffs out the star, it could engulf the second planet, and then the second planet. It will also eject a bit of mass, and it will radiate. There's lots of stuff going on here. But the idea is that it engulfs the planet, which is the planet that's actually observed, and that planet spirals in until the rest of the envelope is ejected. And so it only has to eject a small portion of the binding energy. Now, Jason already showed this, so I can basically skip this, but this is work from Gabe, just graduated. Now, our model in this paper from this year is very, very simple. It's just analytic. We say, okay, you have alpha prescription, you have the binding energy of the envelope. Then you have change in binding energy during the first common envelope episode. That's the first companion. And it removes some fraction beta 1 of the binding energy. And I've left off the term that it contains the initial separation because it's generally negligible. You can check that. And then you have the second common envelope with the observed planet, and that removes the rest of the binding energy. So beta 1 times plus beta 2 must be equal to 1. So basically we ask the question, okay, how much binding energy can the observed planet remove? And then whatever is left over has to be removed by the original companion that's hypothetical. And based on that, we can calculate the mass of that original companion as a function of the mass of the observed companion. And we make some assumptions. Generally, the core is roughly equal to the observed white dwarf mass, we can assume in most cases. So basically, there are parameters, adjustable parameters are in blue. what we get from the MESA models, which we didn't actually use in our first paper. It was just very basic, and we didn't incorporate detailed models, but now I've started to do that. So that's in green. And then the actual observed data is in red. And, we know, for example, the final separation of the planet very well because it's the period is observed. So we have to think about the evolution. And, first of all, we know that the system's probably less than 10 gigayears old. So we're not talking about a very light progenitor. We're talking about at least 1.4 solar masses. So that restricts the possibilities. It could be RGB, it could be AGB, it could be thermally pulsating AGB. But in each one of these cases, it restricts the mass range because, for example, if it's AGB, then it has to at least expand to a larger radius on the AGB than in the RGB, or else it would have undergone common envelope during the RGB. So there are sort of constraints on that. And then the mass of the white dwarf that we actually observe would be equal to the core mass plus whatever has been accreted. These vertical lines, the dotted one shows the Vandenberg estimate for the white dwarf mass, but the new estimate in this new upcoming paper is shown by the black line, which is a bit larger. And the error range is the blue shading. Okay, so this is the gist of it. We get, this is just one example. We take, for example, an AGB star. And what we get, so first in the upper panel, it shows what fraction of the envelope binding energy is contributed by the observed planet. And alpha could be greater than 1 if you think that you're extra sources of energy. But even then, we get values that are quite small. So for what I think is a more realistic value of alpha of, say, 0.25, we get values of less than 1% of the energy is contributed by the planet, which means that most of the energy had to be contributed by the previous companion that was shredded. And there's, so we calculate two possible final radii for that previous companion. One is the tidal shredding radius. So suppose it goes down to the tidal shredding radius and shreds, and that's all the energy that's injected. Then how massive would it have to be? Or perhaps it accretes, that material then accretes onto the white dwarf, and that would lower the mass requirement because obviously you're getting much more energy out that way. So the thick lines are if it accretes onto the white dwarf, and the thin lines are if it doesn't accrete. Now, Noam has pointed out to me that if it doesn't accrete, you have to eject that additional mass, which could be important for more massive companions. But in any case, you would expect that if we again take 0.25 for our alpha, that the mass would have to be somewhere in between sort of the black thick line and the black thin line to get tidal shredding. If you're too massive, you don't get shredded. And if you're not massive enough, you can't eject. So of the order of 10 Jupiter masses or higher. So we're starting to be in the brown dwarf range. Then the second question is, okay, well, fine, but then you still got to engulf the planet, right? So if you don't engulf the planet, then probably what would happen is the star would expand, it would shrink back down after cooling, and you'd have to wait for it to evolve on gigayear timescales to engulf the planet. So that's not realistic. So we want the first common envelope to engulf the planet. And if the way we looked at that is we just set up a very simple model where we balance the energy, hydrostatic equilibrium. Basically, the original energy is set that equal to the energy after the common envelope plus the energy of some ejecta, whatever ejecta there would be. And you can solve for the radius, so how much expansion, R2 essentially. But the other thing that you have to consider is cooling, because if you expand enough, then the cooling rate will be higher than the energy injection rate by the accretion onto the white dwarf. And so when you do that, you find that actually in most cases, that's the scenario that was probably most relevant. You'll have a balance between heating and cooling essentially, and you can look at the minimum, what the radius would be the minimum of the two different radii that you calculate, the maximum radius neglecting cooling and the radius if you include cooling. And basically this is the formula that we get. It's a very simple model, like I said. It turns out that, so it depends on this parameter T injection and also the temperature of after the common envelope. But otherwise you see that for example, like the same parameters that this beta 2 depended on. Basically, the gist of it is that the easier it is to unbind the envelope, the higher the cooling might be because it's a larger envelope. And so sometimes it's hard to satisfy both constraints that you have to unbind and you also have to expand. For the injection time, one can use the Eddington rate to just simply estimate that based on ungave simulations and just simple ideas about that, about how fast could it accrete. So it might accrete faster than Eddington, but as a conservative estimate, we chose the Eddington rate. And you get expansion that can be up to a factor of a few, depending on the values of these parameters. So it is possible that this, in this scenario, could engulf another planet. And this paper, which is now quite old, but it has detailed one-dimensional models of this sort of scenario, and it shows that you actually can get a lot of expansion. And they even include nuclear energy, which could have different effects, but in some cases it could increase the expansion as well. Okay, so the result is that for companion masses less than about 20 Jupiter masses, most of the expansion will happen after the disruption, and that's what we've assumed in the model. But it is somewhat challenging to get, when we put in the detailed MESA models, to get unbinding and expansion, because the more extended envelopes are easier to unbind, but also cool more rapidly. So if you, so you try one star, it's easy to unbind, but it's harder to expand, or vice versa. The sort of my new thinking is that it might be might have been a more massive companion. And you can also see this nice paper by Kramer et al., which shows that for more massive companions, brown dwarf or M dwarf range, you do see a lot of expansion during the plungeon, and not so much for the smaller mass companions like 10 Jupiter mass. In this case, the expansion will be near adiabatic and cooling can be neglected. It also gets around this problem of the brown dwarf desert, but some people say there is no brown dwarf desert for evolved stars. That's another story. You can have a look at this paper. So perhaps M dwarf companions are more likely, but they can't be too massive, obviously, or it would avoid disruption altogether. And in this case, the accreted mass would become significant for the observed, for adding to the core mass to produce the observed white dwarf mass. So just briefly, I'll show you an old simulation that we did, and I'll focus on this one here, which has an M dwarf companion of 0.25 solar masses. And this is just the plungeon that we've simulated, this black line. But you can see that the planets, so basically the original radius of the star is this white circle. Okay, this is, here I'm showing you a graph at the end of our simulation, 40 days. And the blue is the material that's still bound under our criterion, which includes thermal energy. And the red is material that is unbound. The original radius of the star is the white circle. The original Roche-Lowe, the separation where it undergoes, the separation of the companion where it would have undergone Roche-Lowe overflow is the green circle. So the planet would have to be outside of that, presumably. But you can see that it expands, even by this time in the simulations, it expanded about to the black circle. And so any planet sort of in between these black and green circles would have been engulfed and could potentially spiral to the center.
2 minutes, Luke.
Yeah. Okay, so the summary is that, so I mean, what to say about that previous slide is just that it seems possible that you have a more massive companion and then you can engulf the planet immediately during the plungeon. And that is perhaps a more realistic scenario. You don't have to worry about the brown dwarf desert, etc. Okay, so the summary is that planets are being detected in 1 to 10 day orbits around white dwarfs. There are only 2 examples though at present. This is difficult to explain with a single common envelope scenario. However, Felipe's talk is coming up next, so he might disagree with me on that one. So our proposed scenario is that you have this first common envelope event. It begins to unbind the envelope, and then 2 things happen. 1, it can engulf the planet, and 2, the companion is destroyed and accretes. I wasn't very precise about which one happens first. I guess both are possible at this point in time. Now, and then eventually the envelope unbinds. This could be because the second planet goes in and unbinds the rest of it, which is what I had mentioned. But the problem with that, and this is another what I believe is a shortcoming of the model is that beta 2 value, that percentage of the original binding energy contributed by the planet, the observed planet, is extremely small in our models. I mean, it's only about a percent typically. So I think that's a bit of that. For me, that's a bit of fine tuning. I think what actually happens is that it sort of goes along for the ride, and it's the original companion and the accretion from that companion that actually ejects the envelope. And somehow, but that means that somehow that you have to explain why the planet doesn't spiral in all the way, you know. So that I have a few explanations for that, but there's no time. But we should hopefully get that out soon, that new paper. So this is basically a summary of it, and I'll take questions. Thank you.
Nice talk, Luke. So I have one comment before we take questions, but just remember to raise your hand, and I'll call on people in the order that they raise their hands. This last point you made, Luke, about the second planet going on for a ride reminds me of something I wanted to say. I meant to say in the earlier slides I had, but I forgot. Which is that if you're close to unbinding, but you just don't quite have enough, and you get down to the point where then you tidally disrupt, that's going to happen around a few times 10 to the 10 centimeters. And so you can still get deeper into the potential well from the disrupted mass. And so you might go another factor of 5 inward in radius, and that liberates energy then that can be used to unbind the envelope. So at that point, even, you can, if you even didn't have this passive planet too, and you just had the first planet, what you would see is you'd see a single white dwarf emerge on the other side. It might be a bit under massive, depending on the evolutionary state. And I would call it like a post-common envelope system, but how would you know, right? There's no companion left at that point. And so that's, I think, is sort of an interesting point.
Yeah, okay. It's possible. I should say that it's possible that that beta 2 being low is fine, because this is a rare kind of system, but it's also possible that the planet doesn't actually contribute much.
Okay, no.
Yeah, I wonder, about the energetic. It can work, but I think it should be a chain of events, because if you take a companion and let it spiral all the way in to unbind the envelope, the first one that you destroy, then its mass becomes a new envelope. But it can work, I think, because it is initially very compact envelope. Slowly it absorbs the nuclear energy that the core actually liberates, and it expands to form another envelope, but now of lower mass. So you start with some mass of the envelope. I don't know, say you start here 0.4 solar mass as an example. And then the companion spiraling, it's only 0.05 solar masses. And because it comes to smaller radius, it unbinds the envelope, it expands it first, so the planet spirals in, but not all the way in. And then you destroy the brown dwarf, but you get energy now from the nuclear burning to inflate a new envelope that again engulfs the planet, but now the envelope mass is only 0.05 solar mass, which the planet might unbind by itself. So it's a nice work, but I think the energetic should be done very carefully. This is my point. But it can work, using the nuclear burning actually to inflate a new envelope of lower mass.
Yeah, nuclear burning could be important. How much of that material accretes?
Not accreting, just a regular nuclear burning of the core of whatever. You just absorb the luminosity and inflate it, even if you accrete nothing, just destroy it tidally.
Right, so...
It just takes time to inflate, and then you engulf the planet again, but now the envelope is only, 10% of the initial envelope, and a planet of 0.01 solar mass can now spiraling and unbind this envelope, which you use the energy of the just regular nuclear burning in the core. It takes time, but it's to inflate the envelope, but this is fine.
So you're saying that the first one ejects the envelope, but then it itself, after it disrupts, it itself has to be ejected by the...
Yes, and then you stop. The chain of event is complicated. First, you engulf the first planet, the brown dwarf, then it inflates the envelope to engulf the planet, but in a short time, because the inner one is short time, it ejects the envelope. So the planet stops spiraling in. Then you destroy the brown dwarf, and slowly, using the nuclear energy, you inflate a large envelope, is low binding energy. Now the planets enter to a low mass envelope. So the chain of events, maybe it's not common, but you need to do it right to use the energy of the brown dwarf, because if you destroy it, then you have another envelope. How do you?
Well, I mean, if you accrete it, you don't have that problem. So another question,
you cannot
how much
accrete because then you start burning. So it's another. So that your core might be too massive. I don't know. You cannot burn it too fast, and if you liberate energy, you inflate it. So you can burn a little bit of it and inflate it faster. This is also fine, but I don't think you can accrete 0.05 solar mass, because this is a huge energy if you burn it. The hydrogen rich, it's a brown dwarf. So this is my point about the chain of event, which I think should be done very carefully.
All right, let's Paul.
Hi, Luke. Nice talk. Very interesting mechanism. So these planets are massive enough that they might have influenced each other's formation originally from the protoplanetary disk. And I'm wondering, do we have enough observational statistics on exoplanet systems now where we could estimate how common this scenario might be?
You mean in terms of how close the planets?
Yeah, exactly.
I've had a brief look. I'm certainly not an expert on the data, but I had a brief look, and it seems like such systems could exist around. Planets can be much closer in than is typical for our solar system, for example, right? The hot Jupiters and so on.
Right.
But and there are even systems where you can have multiple planets that are close in. At least I've seen a couple of examples, but I can't really. Maybe someone else could comment more on the frequency and the relative statistics if anyone knows.
Yeah, because I think that the selection effects favor the detection of systems like this, and so our statistics should be most complete for them, I would think.
Yeah, Paul, when we started this project, the first pass through the model, I went to exoplanet.eu, and there were a handful of these things that sort of fit the criteria, I think on the order of like 10 to 20-ish. But then the question is the rate and exactly which of these, because this is a very rare system. So there were some out there that sort of fit the general criteria, but it's difficult, I think, to connect to the rates.
Okay, thanks.
Okay, then we had Diego.
Yeah, so with your model, can you give like broad estimates of how much of the envelope is unbinded with the first object, and then how much is unbinded with the planet, with the second planet?
Yeah, so that's what those beta numbers were, so beta 1 and beta 2. So we get like 99% or sometimes even more of the envelope is typically unbinded. Now it depends on alpha, right? So if you assume an alpha of 0.25, say, then it's typically over 99% of the binding energy, not the mass, but the binding energy is contributed by the first companion. There's another way of doing it where you say, okay, well, it's the whole thing that's contributed by the first companion, and the second companion, the planet that we observe, it spirals in, and then when the envelope is ejected, it stops. And just by selection effects, we're going to see the ones that are close by because you rely on eclipses. And if you look at, most of the in-spiral would be at larger radii. But if you look at the ratio and the scaling, you find that when you take into account selection effects, you're much more likely to see it at small radius. So in that case, we would predict that there'd be a lot more planets orbiting, still post-CE planets systems, but orbiting at much larger radii. Another possibility is that it comes down and the planet stops because stops in spiraling. One possibility is that it encounters the disk of that disrupted material from the first companion, and it forms a gap, and because of the viscous spreading, it wants to be pushed outwards by the disk and inwards by the dynamical friction and hydrodynamic drag, and there's some kind of balance set up. I mean, we've calculated that could work too. or maybe just the envelope is so spun up in the interior from the first companion that you have a huge reduction in drag. So these are all possibilities, obviously speculative, but yeah.
Okay. Nice talk, nice model.
Thank you.
Okay, thanks, Luke. Okay, so Philippe, I think you're good to share your slides. Okay, great. I'll give you a 2-minute warning. You might be muted, or at least I can't hear you. No. Oh, you're muted. You're muted.
Now, can you hear me?
Yep, perfect.
Yeah, right, super. So now can you see the screen, right?
Yep.
Yeah, great. Sorry for the little problem. So, hello everyone. First of all, I would like to thank the organizer for the opportunity to present this research. So in this work, we studied the case of WD 1856b, which, as Luke previously pointed out, is a close giant planet candidate or orbiting a white dwarf with a period of 1.4 days. So to put a bit of context, this planet candidate was first detected by TESS, and then the transit was confirmed with the Carlos Sanchez telescope, the Gran Telescopio Canarias, and also Spitzer, indicated at the end that a planet or a very low mass brown dwarf is orbiting the white dwarf. So this discovery was published in Nature last year on September, exactly 1 year, by Van der Voorde et al. So the white dwarf is part of a hierarchical triple system in which it is orbited by a M-dwarf binary located at more or less 1,500 AU. So in this cartoon from O'Connor et al., we can see the hierarchical configuration with the white dwarf here and the planet candidate here. So, in this table, we can see the main properties of the system. The most important characteristics here are the mass of the white dwarf, the cooling time of the white dwarf, which is the time it takes for the white dwarf to cool down to its current temperature since its formation, and the orbital period of the planet. Furthermore, using the kinematics of the system, they conclude that it is likely part of the thin disk of the galaxy, which marks an upper limit for its total age of 10 gigayears. And they also derive an upper limit to the mass of the giant planet candidate of 14 Jupiter masses. So now, the big question about this planet candidate is how it reached such a very close orbit. So in order to avoid its destruction during the metamorphosis of its hot star into a white dwarf, the planet must have been farther than at least more or less 1 AU. So in this context, Van der Voorde et al. Discussed several evolutionary scenarios that could migrate the planet inward, including dynamical instability in a planetary system where the host star evolved into a white dwarf, also CEPO, cosine of oscillations produced by the M-dwarf binary, and finally, common envelope evolution. So the first two scenarios produce changes in the planet eccentricity, which combined with tidal dissipation in or close to the periastro, reduce the planet's semi-major axis. In the last scenario, once the host star evolved off the main sequence and overfilled its Roche lobe, its envelope expand and engulf the planet. Then the friction between the planet and the envelope transfer orbital energy to the envelope, reducing the final orbital separation and ejecting the envelope. This is the perfect classical scenario for a common envelope evolution, as we know. So, through embodied simulations, Van der Voorde found that the most likely explanation for the short orbital period of the planet is the dynamical instability scenario, which is efficient for low planetary masses from super Earth to Saturn masses. For the CEPO cosine scenario, they found that in its current configuration, this mechanism is not strong enough to produce high eccentricity values, While for the common envelope scenario, they found that the orbital energy available to eject the envelope was simply not enough. But however, a more detailed analysis made by these three works here showed that the CEPO COSI-LIDOV scenario can indeed explain the close orbit of the planet. And in the case of Muñoz and Petrovic 2020, under this CEPO scenario, they predicted a mass between 0.7 and 3 Jupiter masses for the planet candidate. So in the same line, we showed that the tight orbit of the planet can be also explained with a more detailed reconstruction of the common envelope phase. Well, also, as we know previously in the previous talk, it is also worth mentioning that more recent works, like those carried out by Luke and Merlot et al., showed under different contexts the feasibility of this scenario. So to start, among all the scenarios presented to explain the short orbital period of the planet, the common envelope scenario is the less affected for what we call the age problem. So as I mentioned before, the estimated upper limit for the age of the system is 10 gigayears. And the estimated mass of the white dwarf is between 0.46 and 0.57 solar masses. So based on evolutionary tracks of single star with masses up to 8 solar masses, we found that the time required to form a white dwarf in that mass range, plus the cooling time of the white dwarf derived by Van der Poel, it exceeds the upper limit of 10 gigayear. So this is a critical problem that all of the above scenarios have at some level. However, with the common envelope phase, the growth of the core is truncated and therefore more massive star with a shorter main sequence lifetime can be the progenitors of low mass white dwarf, which reduces the total age of the system. So this equation shows the very well-known energy formalism for the common envelope phase, in which a fraction given by this alpha parameter of the orbital energy released during the common envelope phase should be at least equal to the binding energy of the giant envelope in order to eject it. So all the solutions we found with the code developed by Monika Sorotovic and explained in detail in Sorotovic et al. 2010, which is based on the binary stellar evolution code of Hartley, meet this condition. So very briefly, this code works as follows. First, we calculated a grid of stellar evolution tracks with masses up to 8 solar masses. Then, as the core mass of the giant star at the onset of common envelope evolution must have been equal to the white dwarf mass of the post-common envelope system, we first search in the grid for giant star with a core mass equal to the measured white dwarf mass. Now, since we know the radius and the mass of each of the potential white dwarf progenitor stars, we can, for all of them, determine the orbital period or semi-major axis at the onset of common envelope evolution using the mass of the companion in terms of the mass ratio of the system and the equation for the Roche law, for the Roche radius, sorry. So, an important point is we also included in the lambda parameter, which adjusts the binding energy of the envelope according to the mass and evolutionary stage of the giant, the recombination energy, which in turn might contribute to eject the envelope during its expansion. So finally, using the main sequence lifetime derived by the code and the white dwarf cooling tracks of Bedard et al. 2020, we can calculate the total age of the system. So the final result of our work are summarized in these figures that compare the total age of the system with the mass of the white dwarf. Well, according to Van der Poel et al., the white dwarf atmosphere is most likely a mixture of hydrogen and helium. So we use two limiting cases for the composition of the atmosphere, a pure helium and a pure hydrogen atmosphere. Well, so about the figures, the red lines represent the age of the thin disk here, and the age of the universe. The black line represents the best fit for the mass of the white dwarf, and the blue line is the age of the white dwarf, assuming single stellar evolution. The black area represents a common envelope evolution without considering recombination energy. The gray area is the same, but using up to 10% of recombination energy, and the dashed gray area is assuming the use of up to 100% of recombination energy. So all the solutions we found using up to 10% of recombination energy and with age less than 10 gigayears eject the envelope during the thermally pulsating AGV, and the orbital separation at the common envelope onset is between 1.7 and 2.3, 2.4 AU, depending on the atmosphere model used. So you can see that since we found solutions below this red line, and these solutions fit better the discrepancy between the white dwarf mass and the age of the system compared to single stellar evolution models, the common envelope evolution is at least as likely as the planet-planet scattering or the CEPO oscillation scenarios. And well, an important point is that we choose this up to 10% of recombination energy value based on two post-common envelope binaries, IKPEG and KOI3278, which long orbital periods can be all explained by including up to 10% of recombination energy or another source of energy. So we put this arbitrary limit of 10% based on these two post-common envelope binaries. And also an important point is that for this solution, we assume a planet mass of 14 Jupiter masses, which is the upper limit derived by Van der Waals. We found that for planets with masses below 5 Jupiter masses, the common envelope scenario is not possible. And well, about the atmosphere composition of the white dwarf, more recent work by Alonso et al. 2021 confirmed that the presence of an H-alpha absorption line leading to a DA white dwarf classification. So this support even more the common envelope scenario. They also estimated, based on the slope of the planet transmission spectrum, a lower limit for the mass of the planet candidate of 4.4 Jupiter masses at 1 sigma level. So also under this assumption, this lower limit also favors the common envelope scenario over the CEPO or the dynamical scattering scenario in a planetary system. Finally, we also found that previous to the common envelope phase, CEPO oscillations could help the planet to migrate inward at the separation required for the common envelope evolution. In this figure, we can see that for the particular case of a white dwarf progenitor with mass of about 1.7 solar masses orbited by a planet with 14 Jupiter masses, the eccentricity oscillations induced by the M dwarf binary can migrate the planet to the required separation to experience Reuchlov overflow in the AGV or the thermally pulsating AGV. Also, we also found that the planet would not be evaporated during the common envelope, and that the mass loss rate of the planet due to extreme UV radiation produced by the white dwarf immediately after the envelope ejection is negligible. So, as a final conclusions, the two most important is that common envelope evolution represents a reasonable scenario for the observed orbit of the planet candidate if another source of energy involving the ejection of the envelope is taken into account. In this particular case, we use recombination energy. As Luke previously mentioned, could be a multiplanetary system, or in the case of the work of Merlot et al., it could be a wave induced by convection during the red giant branch. Also a better estimate of the mass of the planet and the white dwarf can provide more clues about the evolutionary history of this planet candidate. So that's all. Thank you very much.
Very nice talk. I enjoyed that quite a lot. Do we have questions?
So you need it to be on the AGB, the star, because you need low binding energy of the envelope. Am I right?
Exactly. Yes.
And you can get also, okay, and you can get the right mass of the white dwarf. Okay.
Yes.
Okay.
Okay.
Yeah, so I'm trying to understand. You're trying to really explain the discrepancy between the cooling age of the white dwarf and the age of the system, which is measured by what? By its distance from the galactic disk. What's the age measurement again?
It's based on the kinematics of the system. They conclude that it's most likely part of the thin disk. So they took an upper limit of 10 gigayear. So we use this measurement to make.
But there's a huge error bar on the kinematic age. A huge.
Yes.
I mean, for once, it's very relevant for many systems, but for one system, the error bar is huge. Did people try to get maybe a very good photometric from the companions and get oscillosystemology, for example?
As far as I know, there are no more works trying to get a better estimate of the age, but in fact could be a very important measurement to constrain even more if this common envelope evolution is a possible mechanism compared to this single stellar evolution channels.
Okay, no, I understand, of course, but I'm just wondering whether we actually really need to explain the discrepancy. I'm not sure. How strong is that?
Yes, but independently of the age, well, we use this age problem as a point that favor the common envelope evolution. But even without taking into account this age problem, the main point is that common envelope evolution is a possible explanation to the orbit. So
I agree. Thanks.
You're welcome.
Yeah, I mean, you still have the age of the universe, right? So it's still below that on your plots, but Luke?
Yeah, thanks for the talk. Couple of questions. What do you need the orbital, like the alpha for the orbital energy efficiency to be? I forget. And also, what is the mass of the envelope at that point where you have the common envelope phase?
About the exact number of alpha, if I remember well, it depends, but it's about 0.36, about 0.56%, up to 100% of the orbital energy. About the envelope of the mass, I don't remember very well, but well, as we only found solution during the thermally pulsating AGV, it's a very it has a very expanded envelope. It lost plenty of the mass in the envelope mass. I don't remember the exact number. Maybe I can check those numbers later and maybe discuss it in the final discussion.
Okay, thanks.
But I remember the alpha. The alpha is about 0.56.
No?
Yes, Felipe, can you allow me to share something that you mentioned, the scenario we worked on? So
yes, I stop the screen, sharing the screen.
good.
Yeah, and that's sufficient. Yep.
Okay, so I would like to just mention our scenario. It's a speculative one. We took the idea from people who suggested that core collapse supernovae before the collapse can be a few years up to few hours before collapse because of the large nuclear burning have a strong convection in the core, which cause expansion of wave or propagation of wave to the envelope. So we speculated that if we use the same formula, we can use it maybe in core helium flash on the upper red giant band, just as the star is about to leave the red giant band because it ignited the helium in the core. And the formula you see is the formula number 1, and the convective luminosity in the core reach a huge value of 10 to the 8 solar luminosity. This is the convection. And about 1% can go to wave to the envelope if the behavior is as much as people suggested for massive star. And then if you look, you have the time of in years. So for about 4 years, the luminosity of the wave can get very high, to be 10 to the 7 even, because the luminosity of the core helium flash reaches 10 to the 10. And if we use this formula, we find the envelope to expand. It depends how much energy we take. If we take this wave energy, it expands with factor of 3 and can engulf a planet. Now the binding energy of the envelope is very low and it can spiral in and cause this contraction of the envelope in addition to the regular contraction, because now after helium core flash, the core expands and the envelope contracts. I admit it's a speculative one. The question here, does indeed convection due to core helium flash with this huge convective luminosity can excite waves that propagate to the envelope, deposit their energy in the envelope, and cause expansion. But if this happens, the star can expand a lot for a very short time. It takes few years, and it can go off the planets and contracts back on a dynamical time. This is it. And we wanted to explain the same system as previous 2 talks by Luke and Felipe.
Okay, maybe Alexei will be the last question.
Yeah, right. Thank you. And Felipe, thank you for the wonderful talk. And so I was just wondering, because like yesterday, we've heard a talk by Andrei Igoshev, who was saying that, if you have a common envelope system and a triple companion, the triple companion gets in a wider orbit. I could also imagine, if you have common envelope and it happens quickly enough, the triple companion might have been initially eccentric and then lose eccentricity. For example, it was at a fast run, we lose mass and then it becomes circular. So the question really is like, is the orbit of this outer binary in any way statistically slightly different from average? I mean, I know it's it's hard to say, but I mean, like, is it possible to say that is its eccentricity or semi-major axis in any way is different from typical triples or typical outer binaries of such wide dwarfs?
Sorry, can you repeat the question?
So I'm basically asking if one could say whether the outer binary in this triple is in any ways unusual compared to otherwise similar triples.
Well, I don't really know. I don't. Well, I'm working on a survey that the same survey that Stefania and Hernandez presented. I'm characterizing contaminations in that post-cone envelope binary candidate sample, and I found that most of the contaminants are in hierarchical triple system, and in most of them, the white dwarf is the third companion. So if we turn around this system, the white dwarf is the outer companion. So maybe it's a typical configuration.
Interesting.
As well, I also I have a paper that we estimate the fraction of contaminants, in particular triple system with white dwarf and M dwarf, and I found that most of our expected contaminants are the configuration located the white dwarf as the triple companion. So about 80% of the expected contaminants in this particular configuration, the white dwarf is the outer companion, and only in 20% the white dwarf is in the inner orbit. That maybe could be a potential common envelope binaries in triple system or supernovae 1A progenitors in triple system. Although I know that based on works of Sylvia and Adrian Hammers, the contribution of supernovae progenitors from triple system is very low. So, which matches the statistic that I derived. So, yes.
Thank you so much.
Okay, great. So let's take a 10-minute break and we'll start back up at 7:15 UTC. Turn on. Perfect. Okay, go ahead.
Thanks. Hello, everyone. First of all, I would like to thank the organizers for giving me this opportunity. My name is Semih, and I'm a master's student at University of Potsdam under the supervision of Dr. Nicole Rangel and Professor Dr. Stefan Geyer. Today, I'm going to talk about a new class of variable white dwarfs and their mysterious nature, and which could be possibly post-common envelope binaries. And in my I'm working on my master thesis right now, and I'm investigating that. So without further ado, let's begin. Early stages of white dwarf cooling occurs quite rapidly. Only a tiny fraction of white dwarfs have effective temperatures above 65,000 Kelvin. Hot white dwarfs cover a large but sparsely populated area in HR diagram, and there are important links between post-AGB stars and the remaining of the white dwarf cooling track. Therefore, a better understanding of these objects are highly desirable. Among the hottest white dwarfs, an interesting phenomenon occurs, which is white dwarfs showing ultra-highly excited metals in their optical spectra. These objects were discovered nearly 3 decades ago, and previous to that, these features have never been observed in any other astrophysical object. Here you can see 3 different spectra. In the first one, you see a normal DO white dwarf, and you see that the blue lines represent the observations and the red lines represent the models. And as you can see in the first one, the observations match the models quite nicely. In the second one, helium-2 lines are stronger than the model predicts. And in the third one, in addition to strong helium-2 lines, the spectrum shows ultra-highly excited metals. A unique assignment of these lines to particular elements are not possible, but they probably originate from carbon, nitrogen, oxygen, or neon. And due to their asymmetrical shapes, it was suggested that these lines originate from a hot optically thick stellar wind. Therefore, they are also known as hot wind white dwarfs. Here, some of the ionization energies for different ionization stages are listed. In order to achieve these ions, temperatures required are order of 1,000,000 Kelvin. However, these temperatures far exceed stellar effective temperatures. Therefore, a photospheric origin for these features can be ruled out. In 2019, Randall and collaborators published interesting results. For the first time, they detected rapid variations of equivalent widths of ultra-high excitation lines for this particular object, which is shown here in yellow. And they also reported that these variations are correlated to photometric period, which is shown here in red. They argued that ultra-high excitation features originate from a co-rotating, shock-heated circumstellar magnetosphere. Such magnetospheres are commonly observed in magnetic O and B type main sequence stars, and they are formed by trapping the wind material. The wind material is accelerated in the closed magnetic loops, and it collides in the opposite foot points of closed magnetic loops. This creates magnetically confined wind shocks, and these shocks heat up the plasma to several million Kelvin, which is required to observe ultra-high excitation features. But this leaves us with some questions. So is photometric variability common among the other ultra-high excitation white dwarfs? Is observed correlation between equivalent bit variation and photometric period common among our sample? What causes the photometric variability? To answer some of these questions, we conducted a multi-band photometric study. We investigated light curves from ground-based and space-based surveys of 16 ultra-high excitation and 8 helium-2 line problem white dwarfs. Here you can see ultra-high excitation white dwarfs and helium-2 line problem white dwarfs come with different light curve shapes. Some of them are familiar with their roughly sinusoidal shapes, and some of them have extended almost flat minima, and some of them have unusual asymmetrical light curve shapes. Our study showed that ultra-high excitation and helium-2 line problem white dwarfs have high variability rate, and this marks them as a new class of variable white dwarfs. Their periods range from 0.22 days to 2.93 days, and their period distribution agrees with both orbital period distribution of post-common envelope binaries and rotational period distribution of magnetic white dwarfs, if we assume that our young white dwarfs will spin up due to further contraction on the white dwarf cooling. And also their amplitudes range from 0.02 Mach to 0.3 Mach. Here you can see a Gaia color magnetic diagram. Star symbols represent ultra-high excitation white dwarfs, and diamond symbols represent helium-2 line problem white dwarfs. As you can see, our sample resides on top of the white dwarf banana, and they're clearly separated from hot subdwarf cloud. And ultra-high excitation and helium-2 line problem white dwarfs overlap on a region in Gaia color magnitude diagram between these color and absolute magnitude values. They show similar variability rates, period distributions, amplitudes, and light curve shapes. Due to aforementioned reasons, we concluded that these two kinds of objects are in fact related. So what causes the photometric variability? Due to good agreement with the period distribution, a fair assumption would be post-common envelope binaries, and a reflection or irradiation effect system can explain the photometric variability. The second scenario would be photometric variability due to geometrical effects of magnetosphere and spots on the white dwarfs. So what do these two scenarios predict? With the reflection effect scenario, we would expect amplitude increase towards longer wavelengths in the light curves, and we would also expect RV variations in the spectra. For the magnetosphere model, we would expect equivalent bit changes for only photometrically variable objects, and we would expect these equivalent bit variations to be correlated to their respective light curves. The main goal of my master thesis is to shed some light on what causes the photometric variability. For this, I examined the light curves and searched for amplitude changes in different bands. Then I measured equivalent widths and checked for a correlation with their respective light curves. And finally, I searched for RV variability. In our recent study, we investigated all known ultra-high excitation white dwarfs, and we did not see any noticeable differences in amplitudes observed in different bands. However, two new objects were discovered in the white dwarf, bright white dwarf survey, and for these two objects, we also do not see any amplitude differences, and they all agree. However, I should also mention that J0706 show an asymmetrical light curve shape, as you can see here, which cannot be explained with binarity since we would expect symmetrical light curves. In fact, this can be explained with asymmetrically distributed magnetosphere or spots on the white dwarfs. After the photometric study, I checked the spectra. For this study, I used several data from several instruments, but mainly from STSS and twin spectrograph on Color Alto Observatory. Here you can see spectra of J0146 in different phases. As you can see, this particular ultra-high excitation line at 6006 angstrom changes with respect to photometric periods, and we would like to know that if this is common among the other ultra-high excitation white dwarfs. I measured equivalent widths of ultra-high excitation lines, selected ultra-high excitation lines in our sample. However, I could only find a clear correlation for the object J0146, and for the other objects, equivalent width variations are statistically not significant. However, I should also mention that for the other objects, we do not have high signal-to-noise spectra that is essential for accurate equivalent with measurements. That's why we need better signal-to-noise spectra to reach a conclusion. And finally, I searched for RV variability by doing cross-correlation with IRAF's effect score package. By fitting a Gaussian to cross-correlation function, I calculated relative RVs. Here, some of the maximum RV shifts are listed, and I also calculated minimum companion mass with binary mass function. For this, I assumed a typical white dwarf mass of 0.6 solar mass, an inclination angle of 90 degrees, and radial velocity amplitude as maximum RV shift, and photometric period as a period. And as you can see, for both kind of objects, minimum companion masses are substellar. Here I show an example RV variability plot. As you can see, RV variations are quite small, and I would like to know if the RV variations are statistically significant. For this, I calculated false detection probability for each object. However, according to this calculation, no significant RV variations have been found. So to summarize my results, in the photometric study, I did not find any amplitudes towards longer wavelengths. amplitude increase towards longer wavelengths, which would indicate reflection effect binaries. There is no spectral features of indication of spectral features of cool companion, no emission lines arising from heated side of the cool companion. There is only significant equivalent variations for J0146. However, for the other objects, we need better spectra to reach a conclusion. And finally, in our RV variation, search for RV variation did not conclude a significant RV variation, which would definitely confirm binarity. Considering all of the results, we think that binarity is highly unlikely. Instead, we believe that photometric variability is caused by weak magnetic fields. And the final takeaway is that when you find variable stars in this region between these color and absolute magnitude values on time scales typical for post-common envelope systems, roughly 10% belong to ultra-high excitation or helium-2 line problem white dwarfs. And variability is most likely due to not binaries, but linked to big magnetic fields. And so please keep in mind that when the close binary fractions are calculated, or when a new variable star is discovered in Gaia color magnetic diagram. Thank you very much for your attention, and I'm happy to answer your questions.
Very nice talk. Do we have questions? Oh, we have one from Bruce here in the chat. He's saying, is it possible that the white dwarf is tumbling and its field orientation and outflows change in inclination?
I'm not sure about that.
Nicole.
I can comment on the question before. So the idea of this magnetosphere model is that it's oblique rotator, so the magnetic field axis and the rotational axis are inclined, and in course of that, you see the material that is spinning different amounts, once like this part of the magnetosphere and one's edge on, and by that you could in principle explain the equivalent with changes and also the photometric changes, and it's similar to what is observed for the O and B type stars. But in the end, what will be crucial is that we are able to get time to measure the magnetic fields actually.
Do we have any other questions? Great. Well, let's thanks Emma again for a nice talk. And Hans, you are the last talk of the conference. You were supposed to be the first one, but you're going to be the last one. So we're ready when you are.
Okay. Do you see my screen?
Yep.
Okay. So first of all, thanks you all for the very nice conference. And indeed, I'm afraid it is the last talk of the conference, and the topic of the talk is not on binaries that spiral then due to common envelope. So it is a talk about binaries that do avoid common envelope, or at least avoid spiraling in. So I will first introduce the whole set of post-HB binaries in a nutshell, and then I focus mainly on the post-interaction interactions. That these are interactions that happen after the event of the finishing of the HB. These are all my collaborators. I think Akke, you heard in the beginning of the week already. So what are the systems that I will be talking about? So these are optically bright post-AGB star, so they're typically F or K star. You have a dust, and this dust is quite indicative and quite characteristic of those systems because it starts at near sublimation radius. That means that there's hot dust in the system, and that is indicative of a disk, and the disk is in Keplerian rotation. So there are many of them. So in the galaxy, we have about 90 sources. In the LMC and in the SMC, the sample is also large, and we have a few hundreds in the LMC and 100, I think, in the SMC. So you see the typical characteristic of a dust excess, which is quite extensive. So you capture about 30% of the light, and you re-emit in the infrared. And you typically start near sublimation radius. How do we know that they are binaries? Well, we measure them, we follow them with our telescope, and it's handy to have our own telescope. So we have a telescope on the Canaries with a good spectrograph, and it's about a decade that we follow those systems. So they range from orbits from 100 days to 500 days, 200 days, 1,000, 200 days, up to a few thousand days. So the specificity is that they are eccentric, but orbits of around 150 to 2,500, so they certainly did not spiral in, but yet they are in orbits too short to accommodate an AGB star with the same luminosity as we see them having today with the distances we have from Gaia. Of course, there is some uncertainty with the distances, but still most of the orbits are too short to accommodate an AGB star. That means that they have to have gone through a phase of very strong interaction at the AGB. So the evolution is really determined by binary interaction process. Whether it's common envelope or not is unclear, but the orbits now are certainly orbits that we do not expect. So if we see here on the left-hand side, you see a result of a population synthesis, where you of course see a bimodal distribution after the AGB, which are the spiraled in systems that went through common envelope and spiraled in. You have the wide systems, and you don't expect much of the systems at those periods, and that is exactly where we find them. So our distribution is in fact the complete opposite of what you expect from population synthesis theory. So there is certainly some aspects of binary interaction physics that is missing in order to explain those systems. So having a lot of systems helps to do some statistical analysis. And here again, the period eccentricity diagram. If we look at the M2 is of course determined by the inclination. So we have the mass function because they're single line spectroscopic binaries. We have the mass function, but by using the statistical properties of the inclination distribution on the sky, you can have a good estimate on the distribution of the companion mass. And that peaks around 1 solar mass, but we go down to, let's say, a few tenths of a solar mass, up to 3 solar masses. So there is a quite wide spread of companion masses. All of them are main sequence stars. So the companion masses, all of them are still on the main sequence, and I'll come back to that later in the talk. If you look at the separations, and these are mass ratios, so the mass ratios M1 over M2, M1 being the post-AGB star now, which is typically the white dwarf mass, you have a distribution covering in between 0.2 and about 5. And here, this is most important, is of course the separation. This is the total separation, so it's A1 plus A2, and you have a distribution which is again indicative. So you can't put an AGB star in that, so they must have gone through a phase of very strong binary interaction. What we see then is, so the image, so the systems that we see is we have the central binary. I'll come back to the bipolar jet here, and we see a quite extensive, thick circumbinary disk, which is in Keplerian rotation. That disk determines the infrared excess. It's captured about 30% of the total light. And we have the possibility now to resolve the disk because we want to understand the interaction between the disk and the central binary. So we have ALMA probing the outer regions. We have the near-infrared interferometry to resolve the inner rim. And I won't go in too much details about those high spatial resolution imaging because I will focus mainly on the bipolar jet characteristics. Our collaborator Valentin Boucharabal proves that many of them are in Keplerian rotation via interferometric CO measurements. The near-infrared is the region we can obtain now spatial resolution of a few milliarc seconds. So this is in milliarc seconds now, and you really see here the clearly inner rim. The central binary is removed from the interferometric signal. You have several of them now already, and the whole large program was interrupted by COVID. So we reiterate now, and we hope to obtain more of those images to see some, to use the variety of inner rims to study the properties of the disk. Also, one of those projects Akka talked about in the beginning of this week. So stay tuned and that is really the study of that circumbinary disk. Here you see, sometimes we resolve the component, we see light from the component. It's not light from the main sequence star because that's too high contrast, but we observe the disk around the companion. And that's my next slide. So for the next part of my slide, I will really focus on the interaction using the companion as a probe. And in order to do so, I will have to introduce you a few diagnostic plots. So this is time-resolved spectroscopy. That means that we can fold everything on the orbital face. Typically, we show 2 cycles, and one X line is a spectrum. So this is a photospheric line showing the Keplerian rotation. This is a line which is stable to the system, so it follows. It is not moving, but it is rotating around the center of mass. So this is gas in the disk, in fact, that is rotating around the center of mass. But when you look in H alpha, then we see a very characteristic profile variability. So here we see the change in the H alpha profile, and the absorption component, which at high velocity appears when the companion is in front. So when the companion is in front of the luminous OCB star, we see an additional absorption component extending to 300, 400 kilometers per second. So to deploy that in an orbit, we see the main post-ADB star. When the light of that post-ADB star crosses the jet, which is centered around the companion, you see an absorption component, and that absorption component comes from continuum radiation coming from the star that is deflected, or let's say scattered, from the line of sight at the velocity of that Doppler velocity of the jet, of course. So we use the background bright object as a probe of the structure which is ejected from the companion. We have many of those, and in fact, almost all the objects that we have enough data for shows this type of absorption component. Again, this is 2 times the cycle, so it's a bit, we show 2 times the spectra. There is, of course, a variety of absorption components, and it is also a geometric effect, because if depending on the line of sight towards the main star, towards the system, you will have a different topology. So how do we model that? So we model, so this, sorry, that was one slide too fast. A recent example is a protoplanetary nebula, in fact, that is was known as a protoplanetary nebula. We observed it with Rajiv Manik observed it for with SALT telescope. So it's mainly scattered light that you're dominated in. The period is clear, but we also see that absorption component appearing at a quite high velocity. So how do we model that then? In order to know something more about the jet being created around the companion. So we did it in 3 steps. First of all, purely geometric, and we call it spatiokinematic. And the we, you really have to translate to Dylan Bollen, who was a co-tutel student between Macquarie and the university and us. So the first thing we did was a geometric model in which we have a velocity, an angular dependent velocity, an angular dependent density, and we have, of course, the data from the star. We have so we know how big it is. We follow ray tracing through the jet in order to fit that to the spectroscopic data we have. So it is dependent on the jet opening angle, the jet tilt, the angular velocity structure, which means how is the velocity changing with angle, the density structure, and of course the binary components. We did then some radiative transfer in order to show what is the physical expansion of that. So what is the typical mass loss that we find of the jets? And the next step or the next sophistication is that we used models for jets in young star objects in order to see what those MHD jets would imply if we have such a jet in our systems. So just to illustrate how well the fits are. So on the left-hand side, you see the data. On the right-hand side, you see the fit from those geometric models. And you see we do cover most of the structures in all systems. Here you see this on the left-hand side, on the right-hand side, sorry, bottom, you see a system that is always in absorption. That's because we look at almost pole on to that system, and your line of sight always crosses the jet.
2 minutes, Hans.
Yeah, okay, I'll speed up a little bit. So these are the plots that I've shown in the beginning. So what we do, we see that the jet has some angular velocity structure. It's fast in the center and slower at the edge, and you have a density structure accordingly. For every object, we also depend on the inclination because you probe the jet at a different region depending on that inclination. When we did the radiative transfer, we come up to jet velocities of, so the total mass of the jet is 10 to the minus 7, which is quite high, in fact, 10 to the minus 6. It really depends on how much hydrogen do we have in the first excited state. And the mass that is responsible for that accretion really needs to come from the circumbinary disk. The star also moves mass from so the post-CDB star also give rise to mass loss towards the companion, but that's not enough to explain those kind of mass loss rates. So you really need a circumbinary disk to replenish the disk around the companion. So next, we did some physical modeling in the sense that we took models from the MHD physical models from this paper. We translated it into observables. And the data that so it's self-consistent in a way. There are, of course, a few parameters. Magnetization is a parameter, and also the launching region is a parameter. So where the jet is launched within the system. So that was a master thesis of last year. And so the difficulty was, of course, to change our model into observables. Again, this is an example. So this is the star. All the line of sights towards the star will cross the jet in projection. And so you only need to take into account the radial component because that's the one that we observe. And so we manage indeed to, or he manages to come to a solution. We don't fit yet, so that's the next step, but you see the very high mass accretion rates is confirmed. And so we really need some high accretion rate in order to have enough mass in the jet as to explain our spectra. Another thing is that in the models, there is a typical rotation, and that rotation of the jet is seen in a red-shifted component because you rotate, and if you have material coming towards you, you expect a red-shifted absorption component. And in our data, that is never observed. So we don't see a rotating jet. That probably means that the launching region of the jet is quite far away from the central main sequence. So this is work in progress because we do not fit yet. So this is my last slide. So the post-interactions is quite important in those systems to understand them. So first of all, we have to understand how the circumbinary disk is formed. If you have a circumbinary disk, then you very easily make a jet because you accrete material from that circumbinary disk on the jet. And in order to understand those systems, you really have to understand that interplay between the different components. So more of us stay tuned because we have higher angular resolution data and to come up with. And of course, one of the questions is how this disk is formed. The systems evolve in wide systems with a circumbinary disk, which is vital in understanding those systems. Thank you very much.
Wonderful talk, Hans. I'm just going to embarrass myself here for a moment. And so when I was a graduate student, Hans, I remember my very first conference I went to, you gave a talk on this population of objects. And I remember back then, there weren't that many. There were very few. And so to see sort of so many more in the LMC, the SMC, and then also the observations of these have gotten so much better as the modeling. It's just, it's fascinating to see, you know, see the evolution.
I still remember that talk, by the way. So there are more, and it's really a common phenomena. And it's probably also responsible for many, well, if you can replenish the disk, then many of the jets formed in also protoplanetary nebula, where we don't see the center star because it's too much embedded, that is also a viable mechanism there.
Yeah. Let me just ask a quick question here, and then we'll go to Sylvia. So if you go back to your slide where you plotted the mass or the mass ratio, actually the fit to the mass, I think, distribution.
This one?
For the companions. It was one of the first few slides.
Oh, sorry.
Well, one of the things that struck me about it was that, so your companions were going from, I think, like half a solar mass all the way up to 3. Yeah, this one. Or maybe it's a little bit less than that. So, I mean, so a lot of those, I mean, if your average mass is like 1.2, I mean, so your Vol star would be higher mass than that. And so these are, coming from that. But in terms of the eccentricity or the various things versus either the mass ratio, does any of it correlate? So as you go down in mass of the secondary, does anything correlate with that?
No.
Versus mass ratio? No, there's just scatter.
Yeah.
Okay.
There's not much correlation. We looked for many correlations, but we could not find many.
And before we go to Sylvia, actually, a guy has a question in the chat that's similar. Can you show a plot of the separation versus the white dwarf mass?
Say that again.
He wants to know if you can show a plot of the separation versus the white dwarf mass.
The separation versus this one is the separation, but it does not contain. So no, I don't have this figure, but I can make it if you want.
Yeah, I guess the most interesting thing would be actually the pericenter versus not really the mass of the white dwarf. What's really interested is the size of the progenitor on the AGB, probably, just to see whether where exactly should we see a correlation between the disposition and the size of the progenitor.
Yeah, okay. So if you look in this paper, that figure I can't. So I don't have it in my slides, but that figure is there. So that means it's with the luminosity we find now, or there is some uncertainty with the distances, of course. So we are waiting for Gaia 3, but then there is a figure there that shows that almost all of the systems are too small to accommodate the current AGB star.
No, that's for sure.
With the same luminosity.
How deep did they penetrate this?
Okay. I'll yeah. So that figure is there, but it's not in my slides.
Sylvia?
Okay, sorry, I was struggling to unmute for a second. And I just want to also second what Jason was saying, that I think these are such interesting systems, and it's really amazing to see how much progress there's been. So really nice. So
thank you.
My question is about how are these systems selected? So are they selected from the fact that they have a circumbinary disk, or?
Yes.
Okay.
Yes. So yes. And so there are two. So we do have a few systems where that circumbinary disk is vanished, but so yeah. And now I have to go to my last slide. So there is accretion from the circumbinary disk also on the main star, and that leaves a chemical imprint. Mm-hmm. And that chemical imprint is that the dust, so elements that are on dust grains do not accrete, and that means that chemical imprint is very characteristic, and so there is a one-to-one correlation between the chemical imprint and the binarity, and there is also a one. And so all the binaries with the disks are depleted. We call it depletion because the metals are gone from the atmosphere. And we have some objects that are depleted, also in a binary, but and we suspect that the disk has disappeared.
And my very quick second question, if I can put it in there, do you have a handle of the space density?
No. The best way to do so will be to go through the LMC, because there our volume, let's say, is more complete. And so I can't answer it right away, but we have the potential to come to that number.
Yeah, I think that would be interesting for.
Yeah, I fully agree.
Always tough.
Yeah, but so there is a few. So with the disk in the LMC, of course, we don't have all the data. And we don't have the monitoring of the spectra. So we don't have the orbital properties. We have the disks, but we don't have the orbital properties. While here in the galaxy, the distances are a little bit of a problem. And we're not so sure whether we are complete.
Okay, thank you, Hans.
So it's not that straightforward. Now that I think of it, it's because we look on the LMC, the binary orbits, or the distribution of the orbits.
Fabian?
Yeah, thank you so much. I mean, this is wonderful results, and congratulations on all this sort of information coming together.
Thank you. But you have to congratulate the PhD students as well.
Yeah, absolutely, to the whole team. I mean, and this is really beautiful. I just noticed a similarity, and I have no idea whether this is actually connected to your stars or not, but I thought I just wanted to mention this. So there are a few blue stragglers that are observed in open globular clusters that also have really white companions, and these companions, I think, are thought to be white dwarfs. And so the natural question essentially that I would like to ask is, so could your systems here also just be sort of the precursor stage of these blue stragglers? And so the accreting star that you have in your system that accretes from the circumbinary disk and maybe launches a jet is just an object that sort of has accreted from the companion, sort of from your post-AGB star. And at least in the way I think, but my latest, well, I haven't followed this field of these blue stragglers in clusters, not for the last couple of years, but the idea was that these systems could maybe just undergo stable mass transfer from a giant or an AGB star, and that maybe the parameter space for having stable mass transfer is larger than what you usually assume, for example, in all these population synthesis codes, because the codes are relatively simple, right? You assume essentially fully convective stars and so on, and then you come up with the stability criterion. But if you have sort of these other structures, and things might be a bit different.
Yeah, well, I don't know how much mass is accreted though. So so for our systems, we have a good handle on how much mass is accreted, because the photosphere is depleted, and then you can use that as a probe of how much mass is accreted. But but that's not a lot, eh?
Yeah.
Because in a post-AGB star, the envelope mass is a few hundredths of a solar mass only, so you can easily change that into a chemical peculiar object by not accreting a lot.
Absolutely, and also I guess if there was stable mass transfer, then I guess this would be highly non-conservative, given that you must have been in a wide system, and so you would accrete via a disk actually in this mass transfer phase. Yeah, and but that would also make some predictions on the spins probably on the star that is now emitting the jet. And the predictions, I guess, would be that it is maximally or almost close to critical rotation.
Yeah, so we in our system we don't probe that star. So we probe the circumcompanion accretion disk, and we resolve it with the interferometer, but we don't probe the center star because it's not luminous. So we don't have a spectrum of the center of the companion mass. I mean, or the companion.
Okay, now.
Yes, I would like to make 3 short points. First of all, before the points, I think the discovery of the jet, Hans, it's a really beautiful work, a breakthrough. And my 3 points is first, 15 years ago, I tried to compare the red rectangle, which you are familiar with, is Eta Carina. And now, clearly, the red rectangle is shaped by jets, and people still arguing for Eta Carina for equatorial ejection and collimation. I don't think it's work. I think also Eta Carina is shaped by jets, but this happens 200 years ago, so we will not detect it now. Second point, I think my view is that these systems are potential for the grazing envelope evolution.
Yes.
You see the ingredients that they must have been, really strongly interacting with the envelope, maybe even evolving inside the envelope, on the outskirts of the envelope, and we see the possibility of jet. Third comment, I was arguing, I'm still arguing. There's a new paper I submitted and which was accepted by AstroPH, and now it's in the journal. But I argue that all the detection of jet rotation by young stellar object people are not real rotation, and I even said I will challenge every detection of rotation in jet, and I will claim it's not rotation. The last one was a month ago. So I think you will not detect rotation. Don't look for rotation. Their model, I think, is problematic. Say it's, soft way, it's problematic. Don't expect rotation. And I bet you will not detect rotation, and it's not a problem. You have an equation disk, you have jets, but you will not detect rotation. You can look at my paper, and it's recently by myself. I just submitted an AstroPH that I say, jet precession or something instead of jet rotation in one specific object. Look for it in the archive. It's just a month ago, 2 months ago, I don't know. Okay, so I don't think I don't think that it's a problem that you don't find rotation. You can apply the model, but
I can confirm that we don't find rotation, at least not at the velocities that we would see the redshifted absorption component. So this is the model, and we never see this kind of if you go to the data.
Yeah, and I don't expect you will detect rotation.
You never see.
I think they predict much too high rotation. And look at my paper, which I cite earlier paper. So it's not a problem, I think. Very good work. Thank you.
Thank you.
Okay, I don't see any more questions, and it's almost 2. So Noam, do you want to do a wrap up? You're muted. We can't hear you now. You're still muted now.
I'm muted, but I hear myself, which is great. I talk and you don't hear me. I think we are, you are my wife. So I would give 1 or 2 minutes to people. Really, if somebody would like to come with something and didn't have the courage till now, just to raise something. We can wait 1 or 2 minutes and just to see some young people, somebody general comment, because this is the last session and we are recording this session. So it will be, people will watch it and you can watch it later. So if you have something, I really encourage, if somebody has something to say, general.
I can also suggest what we did in some conferences that I organized, is that people are interested just to mention in 1 or 2 sentences something interesting that they learned, not necessarily the most important, but something that was interesting for them or exciting, whatever, just in 1 sentence on whatever topic or talk or anything.
Tomek, we don't hear you for some reason. I don't hear you. I don't hear you. Maybe somebody else. Yeah. So Tomek has something to say. Anybody else? Jason, please lead the discussion. It's your session. Is Jason here? Yeah.
Yes, I also have a hard stop at 2. I have to go to something else, so you're in charge now, no. But Enrique has his hand up, so maybe we should let Enrique say something.
Yeah. Enrique.
Well, thank you very much. This was such a nice meeting. Lots of very interesting topics were discussed. I wanted to probably mention a little bit on some of the discussion that we had on accretion onto black holes. There's, of course, the issues with resolution, which will be probably one of the next challenges for these kind of simulations on accretion onto black holes. My impression is, however, that, well, there's older papers from Rufert et al. From the 90s and many other studies for the next few years, where accretion onto this object seems to be kind of converging. And on that topic, I think accretion onto these kind of objects can be actually hypercritical. And hypercritical, so we were probably focusing a lot on Bondi-Hoyle-Littleton and whether that could lead to these rates of accretion. However, when you are already in the regime of neutrinos, accretion can also be Bondi. And of course, the Eddington limit at that point is not dictated by photons, but by neutrinos. So my impression on that particular area is that you could indeed have very, very large accretion rates without much trouble. Hopefully, numerical studies will come out and show us what's the way on that. So thank you again very much for all the contributions, for organizing this very nice event to all the organizers. It was really, really great. Thanks a lot.
Thank you, Enrique. Anybody else, or we close it because some people already left because they had some plans? We already 40 people. Okay, so Tomek, are you here, Tomek? You want? Okay, so yeah, anybody else? Hans, do you
No,
want to
well, I think it was a very interesting, so I could not follow because with some of the academic stuff, but I heard many interesting, inspiring things. I think we still have a lot to work on the connection between the different groups of the white dwarfs, the post-ABs, the AGBs, and then for the more massive stars, all the zoo of different objects. I think the interconnection is still not very clear to me, but I think that will be very interesting.
I would like to say that the systems that you study, that Ursula called Van Winkel object, and I call them post-AGB, because post-AGB intermediate binaries are I think, belong to the common envelope community because of the interaction, the jets, and the circumbinary disk. Really, I think belongs to this community, because we should be open not only what we think common envelopes are, but also what type of interaction. And all, I think the physics is relevant. This is my point.
Yeah, but I think we still need to connect them to the AGB. So we should look at AGB stars with grazing companions where a jet is present.
Okay, so, okay, thank you. I'm stopping the recording, and thank you everybody who stayed to the end.
Thank you very much.